Hey folks, welcome back to Combo Class, where today we're gonna look at some different types of infinities. You may think that sounds crazy. Why would there be different types of infinity? Infinity is just an endless quantity, bigger than any finite number. Well, mathematically, it does make sense to classify some different types and sizes of infinities. This is not to be confused with a topic we covered earlier in this grade about things that are arbitrarily large, but not actually infinite. In this episode, we'll be looking at quantities that are actually infinitely large, but different sizes than each other. Let's begin by looking at some number lines and wondering about the locations of four important types of number. The square numbers, the natural numbers, which are similar to the whole numbers, very debated whether it includes 0 or not. In this case, we will be including 0 as a natural number. The rational numbers, which include all numbers that can be expressed as a fraction too, and the real numbers, which is basically the whole number line, and it also includes stuff like pi and e. Some of these are classified as having the same amount of infinitely many of them, while others are classified as being different types of infinity. It may seem obvious that there are more natural numbers than square numbers, which we have 0 will include as 0 squared, 1 is 1 squared, and then we don't get another until 4, which is 2 squared, and then 9, and they get more and more spread apart. And it's true that if we look at a finite stretch of number line and look at a trait such as what's known as natural density, what proportion of that stretch of number line had each of these, there would be more natural numbers than square numbers. But what if we look at the whole infinite set of each of these? We can even line up these two infinities where each natural number has a square and each square number has a principal square root that's a natural number. Any square number we can connect to a single natural number, and any natural number we could connect to that singular square number, which is known as having a bijection between these two infinite sets. Now, since this thing called a bijection turns out to be very important in the simplest ways to demonstrate these different types of infinities, let me explain what a bijection means using some finite-sized sets. A set is basically a collection of things, and we were looking at some infinite sets like the natural numbers or the square numbers, but you could also have a set that had a finite amount of members in it. And that could be all sorts of things, from letters. Maybe I have a set that contains A, B, C, and Z. Or maybe I have a finite set of numbers that includes 1, 2, 3, and 31. Or we could even use examples of random real-life things, like let's say that we have a set that contains my 3 cats. And let's say we have another set that contains some amount of bowls of some really yummy special treat for cats. And let's say we have some functions which are which bowl which cat is going to try to eat from. With these functions, we're assuming that every input is going to go to an output, or in other words, each cat is going to go to some bowl. If we have just 2 bowls, and we have a function where these 2 cats eat from that bowl, and this cat eats from the other bowl, this is known as a surjection, because each of our outputs has at least one input that leads to it. Or in our analogy, each bowl has at least one cat eating from it. But what if we had 4 bowls, because we wanted to make sure that there was no problems with the cats having to share their food? Well, if we had 4 bowls, and we had a function where each cat was eating from a different one, and that one would be left empty. This would be known as an injective function because each of our outputs has at most one input leading to it. Or in our analogy, each bowl has at most one cat eating from it. Now, if we had exactly 3 bowls and a function that lined up one cat to one different bowl each, this is both an injective function and a surjective function, and when a function is both, it's known as a bijective function, which we can think about as meaning that each output of some function had exactly one input leading to it, and each input had exactly one output leading to it. Now let's get back to infinite sets and those types of numbers that we were looking at. Now, we were matching square numbers with their principal square roots of natural numbers, but we could do a similar thing with sets that include negative numbers. Like, if I wanted to line up all of the integers just with the natural numbers, I could make some pattern. Like here I could say that each natural number I cut in half and then round up if needed, and if I didn't need to round up, I make it negative. This will create a bijection between all of the integers and the natural numbers. And when we can do that with an infinite set of numbers, we'll consider it countable. Some infinities are separated in their classification as for whether they have a bijection with the natural numbers or not. This type of infinite set that can be counted by lining them up with the natural numbers is given the symbol Aleph 0, also known as Aleph naught or Aleph null. Any infinite subset of the natural numbers, like the prime numbers, for example, has this type of infinitely many of them. But what about other sorts of numbers? Like, what if we wondered about the rational numbers? Every number that could be expressed as a fraction of 2 integers. Do those have this same sort of infinity? If we're trying to biject another infinite set with the natural numbers, it's like we're taking the list of natural numbers and trying to assign a thing to each of them. In this case, a fraction. We're looking at the rational numbers, which are numbers that can be expressed as a fraction of 2 integers. And that does include things like whole numbers, because technically those could be called a fraction, that over 1. And the rational numbers even include the negative versions of these. So how could we take all of the rational numbers and find some pattern that will let them line up with the natural numbers forever? Well, if we started with something like, I'm going to do 1/2, and then I'm going to cover the other things related to halves, like fourths and eighths and other powers of 2. Well, I would go forever before I ever hit the fraction 1/3. So that's not gonna work. However, there are ways we can do this. Like, what if we looked at each fraction's sum of the absolute values of its numerator and denominator? Or in other words, took each of these, made them positive even if they'd been negative, and then added them up. Like the fraction 2/3 would give us 5 there. The fraction -1/12 would give us 13 there. And let's say we began a process with our first rule being that we are going to sort our fractions with these sums in ascending order. The only fraction we would put down first that the numerator and denominator add up to 1 is 0/1, or in other terms, 0. And we are gonna have another rule that whenever we list a fraction, we also then put its negative version. But we don't have to do that in this case because -0 and 0 are the same in almost all branches of math. Now, if we go to the fractions that have a numerator and denominator that add up to 2, we could go for 0 halves, but we are going to have one more rule, which is that if we meet a fraction that is essentially synonymous with a fraction we've seen before and could be simplified, that they are equal, just written in different forms, like 0/1 and 0 halves, or 1/2 and 2/4, that we will skip the fraction we've met for a second time that was a duplicate in a different form. So we don't have to put 0/2, we'll just put 1/1. And we're not going to put 2/0 because I said we're banning zeros from denominators. Now we must also apply our rule of whenever we write down a new fraction, we also put down its negative form. Now, if we look at fractions where the numerator and denominator add up to 3, we have 1/2 and 2/1 as valid options. So we need one final rule, which is that we're going to list the numerators in ascending order when we have multiple fractions with the same sum of components. So first we would go 1/2 and its negative version, and then we would go 2/1, which we know more commonly as the number 2, and its negative version. And if we continued to fractions that have numerators and denominators adding up to 4, we would have 1/3 and -1/3. We wouldn't need 2 halves or -2 halves because those are the same as these. And we'd want 3/1 and -3/1. And even though these are infinite lists, since we found a pattern that lines them up together with a 1-to-1 correlation, that's just one of many ways that we can put all of the rational numbers in a bijection with the natural numbers, meaning that they are also considered as having that same size of infinity, the countable type of infinity, Aleph 0, as the natural numbers. But could we do something similar with all of the real numbers? The whole real number line, not including things like imaginary numbers, but including all of the irrational numbers like pi and e, which can't be written as a fraction of 2 integers, and if you try and write them as a decimal, have an infinite amount of digits after the point, which will never repeat in a periodic way. If we were able to take the rational numbers and put them in a bijection with the natural numbers, can we find a way to do that with the real numbers too? Well, the mathematician Georg Cantor found a very interesting answer to that question, as well as a very interesting way to prove that answer, known as Cantor's diagonalization. Cantor's diagonalization argument, also known as Cantor's diagonal argument. Cantor's diagonalization argument is basically a proof by contradiction, assuming that maybe there was some way to create an ordering or pattern of all of the real numbers lining up in a bijection with all the natural numbers, and then showing that that would result in a contradiction or impossibility. Now, there are many ways to go about this, but let's use the method that looks at numbers only between 0 and 1 and shows that even that tiny slice of the number line, if we include all the real numbers, is impossible to biject with the infinite amount of natural numbers. All of the numbers between 0 and 1 in decimal form are going to be 0 point something. And remember that The rational ones of these will have some periodic pattern at some point that repeats, whereas the irrational numbers that are included within the real numbers will have an infinite amount of decimals that never repeat in a periodic pattern forever. Let's say we did have a way to enumerate all of the real numbers, and here's an example of a list we may have generated to achieve that. These digits I chose randomly, so it may seem arbitrary at first, but bear with me. This is going to show that no list like this could possibly exist. Now, on this potential list of real numbers corresponding with natural numbers, we're going to apply a particular pattern. We're going to go to the top one on the list, take the first digit here after the decimal point in this case, and add 1 to it. And we're going to do a similar thing on the next number, but we're going to go one place over. That 7 turns to an 8. And once again, one place over. We're now 3 after the decimal, turning the 5 to a 6. We can turn the 2 to a 3. And continue this pattern diagonally. After continuing this forever, we could create a new number, which is 0. All the digits on this diagonal, 0.286333138, etc. Now, I know it sounds arbitrary that this is the number we created because I wrote random digits as my examples. But if we had any way of lining up the real numbers with the natural numbers as a bijection, we could do this and create some new diagonal number or another. And this diagonal number cannot be on our list. It couldn't be the millionth item on the list or the billionth or any item on the list because it has one digit different than every single item on the list. No matter which order we tried to put all of the real numbers in, matching them up with natural numbers, we could generate a new number that wasn't on our list. And that shows that the list was incomplete and we hadn't actually been able to match up every real number with a natural number, because this one, for example, or whichever one we generated, couldn't get a number. If it was at some number, well, it had a digit different than what was supposed to be at that number. And so Cantor's diagonalization proof shows that you cannot make a bijection between the real numbers and the natural numbers. This shows that the real numbers should be considered a larger sort of infinity than the natural numbers or square numbers or rational numbers. In fact, here we showed that even the small slice of number line between 0 and 1 can be considered a larger infinity than all of the whole numbers. In fact, if you include real numbers, there are more numbers between 0 and 1/1 billionth than there are the total amount of infinite natural numbers. This is one way of showing that there are some infinite sets that can be put in bijections with each other, and there are other infinite sets that can't. This diagonal is a diagonalization. Cantor's diagonal. Cantor's diagonal. This diagonal theorem shows that you cannot create a bijection between the natural numbers and the real numbers. So unlike the natural numbers and rational numbers, which have an amount known as countably infinite, the real numbers are known to have an uncountably infinite amount of them. Now, once you have Aleph 0 within your system, it ends up making sense to add other Aleph numbers as well, with varying subscripts that say, in simplified terms, how large that type of infinity is. We're entering the land of set theory, which we haven't discussed much on this channel, so I am gonna have to simplify things and still probably won't be able to use as many cat analogies for the rest of the episode, unfortunately. You may just have to go along for the ride as I explain which things mathematicians have proven about these different sorts of infinities and which questions still exist. Within set theory, you can define the Aleph numbers and also define other sorts of infinities, some of which aren't necessarily a member of this hierarchy. For example, the type of infinity that we were discussing as lining up with the real numbers, how many total uncountable real numbers there are, is known to be 2 to the power of Aleph 0. This is because the size, or in set theory terms, cardinality of the real numbers is a power set of the set of natural numbers, which is a concept we can't fully go into today. But what I do want to tell you about is something known as the Continuum Hypothesis, where mathematicians wondered, is this number equal to Aleph 1? Or in other words, is this infinity that represents how many real numbers there are the second smallest infinity? Or is it some other sort of infinity? Maybe even one that doesn't live within this hierarchy. The Continuum Hypothesis, made by that same Georg Cantor, said that these two infinities were equal, and there were no other infinities between them. And the strange thing is that first mathematicians showed that if this was true, it would fit in perfectly fine with all of the other axioms of the currently used model of set theory, ZFC. But then mathematicians proved that if this was false, it would also fit in. In simplified terms, there's a version of set theory that fully works where the continuum hypothesis is true, and a version that fully works where the continuum hypothesis is false. And this is a topic that mathematicians still debate about, because when we decide results are proven, those are dependent on which axioms we built a structure out of. Some mathematicians think that this lack of an answer for the continuum hypothesis means that the ZFC model of set theory doesn't have enough axioms in it, that we might have to add another axiom or something that we take for granted that we base our proofs off, so that the continuum hypothesis could either be provably true or provably false within that system, as opposed to its current state where it's considered independent of the ZFC set theory axioms. Despite the fact that the continuum hypothesis is in this strange state, many things about infinities are still being proven by mathematicians. Some branches of mathematics don't even treat infinity as an allowed thing. But most of the branches of mathematics that do have to not only allow one infinity, but allow an infinite amount of infinities in a hierarchy that we still don't know much about, and is still a very interesting field of research in my opinion. And these concepts like countable and uncountable infinities don't just relate to mathematics, but relate to things like game theory, to geometry, and all sorts of other things. Sometime try and think about different things in your own life that feel infinite, and whether you would think they're closer to an uncountable type of infinity or a countable one? So although mathematically it may feel like infinity is just infinity, it can make sense to define a lot of different sorts of infinities. And I hope you learned some interesting things about that topic with me today. Thank you for joining me in combo class, with a special thanks to the people who help make this show possible, such as my Patreon supporters. I love you all, and I'll catch you in the next one.